302, Physics in Action. I am your host, Ms. Nielsen, and today I am reporting on the phenomenon known as waves. What is a wave? More details to come, stay tuned. Before the break, you completed a web quest diving into the world of waves, oscillations, and vibrations, and today we are clearing up and expanding on those ideas. That's right, folks, you're going to want to take notes on today's report. First, we're going to head over to Mr. Willauer in Studio 328, and he's going to introduce us to wave structure. Then we're going to head over to my classroom 302, and I'll tell you a little bit about wave vocabulary. I repeat once more, you'll want to take notes on today's phenomena. Heading over to you, Mr. Willauer.
Good morning and good afternoon to you physics students. This is your field reporter, Mr. Willauer. Today I'm going to be taking you through some ideas about waves. So we're talking about waves today. Okay, so that's our main topic. What is a wave? A wave is a disturbance that can get from place to place. Okay, that's a very basic definition of what a wave is. And we've got two main categories of wave. We've got mechanical waves, and we have electromagnetic waves. So we're going to use this. As we go along, we will more specifically define this, but at this point we can just talk about some sort of disturbance. So let's talk a little bit more specifically about the difference between mechanical waves and electromagnetic waves. Mechanical waves. What makes a mechanical wave a mechanical wave? Here we're talking about a wave that needs some sort of matter, solid, liquid, or gas, for the disturbance to get from place to place. For the disturbance to get from place to place. That's a mechanical wave. Examples of mechanical waves. Well, one example of a mechanical wave is simply ripples on a pond. You drop a rock in, the rock hits, and then that disturbance gets spread out over the pond. That's one. Another one you have is earthquake, or called seismic waves. When you have an earthquake, the ground itself is what makes the matter that the wave transfers its disturbance through when it gets to the surface. The shaking, the back and forth of that motion is what causes all that damage. Another one we can talk about is sound. Sound is a wave as well. Any sound you have, it's using the air to travel through. If it's in the air, sound will travel quite well in liquids, and it travels very efficiently in solids. Okay. We sometimes refer to the matter here as the medium, and the medium is the material, and again, that could be solid, liquid, or gas, that a mechanical wave uses. There is no sound in space, simply put, because there's no matter there, okay? So these are definition of mechanical wave and some examples of a mechanical wave. Next up, we need to talk about electromagnetic. Electromagnetic waves. The difference between an electromagnetic wave and a mechanical wave, there is no matter required for the disturbance to get from place to place. That's what an electromagnetic wave is. Another way of saying electromagnetic wave, no medium, which means it doesn't, no solid, liquid, or gas, no medium is needed for this. Examples of electromagnetic waves? Well, the first is light. Light does not need a medium to travel back and forth. We don't need that. Another one, X-rays. If you've ever gone to the doctor's office and had an X-ray taken, you don't need any, no medium for the X-rays. Radio waves. Radio waves is a broad number of different waves. Within the radio wave, that's how your cell phone communicates. You could actually have a cell phone, if it had enough power, you could have a cell phone up in space and it would be able to talk to somebody back on Earth because it travels through radio waves. Wouldn't need those types of things. And then we've got some other ones, lesser known ones, gamma rays we could put down. But needless to say, all of these we can put down. We'll talk about this one briefly, infrared rays. Infrared rays are the ones that come from the sun. And those are the things that can give you a sunburn. So the sun can get an electromagnetic wave all the way from the sun, 93 million miles away. I think that's what the distance is. All that energy from the sun can get to you and it can burn your skin. We don't hear the sun because the sound that the sun is producing is a mechanical wave, and there's no matter between the sun and the earth. So mediums, or I should say media, and again, this is solids, liquids, or gases, okay? Media can be disturbed in two ways, okay? Producing two distinct wave forms, okay? So I know that's a lot of words there, but I wanted to talk about what we're doing there because we're talking about a transverse wave and we're talking about a longitudinal wave, okay? So we're going to talk about these. I'm also going to have some examples for you that I'm going to do here in the class. We can talk about what those are. So I'm going to first start off with a transverse wave. In talking about that, let's say that I have a slinky here. So this is transverse. Transverse wave. What does it look like? How is it produced? So let's say that I have a slinky here or some material. I'll be using a slinky in a moment for you. And let's say the slinky is laying on the table like so. Okay, so it's just laying there. That's a terrible picture of a slinky, but hopefully you get the idea, showing the coils as it runs down the line. So right now this slinky is not disturbed. It's just laying there, and I can actually, I'll do it in a different color here. I can actually draw a line, a dotted line, essentially through the center of the slinky. This center line we would call the equilibrium point, or we talk about its equilibrium position, okay? That's what that orange line is here. And that means equilibrium point or equilibrium position. That means that's where the material is, that's where the matter is when it is not being disturbed, okay? That's the equilibrium point or the equilibrium position. In order to produce a transverse wave, I would have to grab the slinky here and I would shake the slinky perpendicular to that equilibrium position, okay? So you'll see a video here in a moment and that'll show that to you. So again, what I'm going to do here is I'm going to shake the slinky back and forth perpendicular to that equilibrium position. And what is the equilibrium position again? That is the position that a medium would be in when no disturbance is affecting it. So one of the types that I mentioned was a transverse wave. So if we watch this, if you go down along this spring here, we would call this the equilibrium position. That's the position matter wants to be when there is no disturbance traveling through it. And now I'm going to do a transverse wave, which means I'm going to disturb it perpendicular to the length of the medium here. And when I do that, we get a transverse wave. Now this is something called a standing transverse wave. We won't worry about that right now. Hard to see, that's really quick. Look at the slow-mo, you might be able to see it a little bit better. Now let's look at a longitudinal wave. And we'll slide this up a little bit so we make sure it's there. And we'll use the slinky here again. That's a terrible slinky. And again, I'm going to put in that equilibrium position. Okay. Again, the dotted line here, equilibrium position. Maybe I should write this up here just so we have it. The equilibrium point or equilibrium position is where the matter or medium is when not disturbed. Okay? Slide that down a little bit so you can see it all. So again, for a longitudinal wave, the difference here is that instead of, you remember for the transverse wave, we're sloshing it perpendicularly to the equilibrium position. For a longitudinal wave, instead of sloshing it back and forth, we're going to slosh it back and forth in the same direction or right in line with the equilibrium position. So we're going to slosh it in this direction, and instead of the spring going up and down, the spring is going to oscillate back and forth in this direction. So you'll see that in this clip.
Thanks, Mr. Willauer, for that awesome description of different types of waves. Now I'm going to take you through some basic wave vocabulary. So let's say I have a standard wave here that goes up and down and up and down, and excuse my terrible drawing ability there. That's a wave, right? Like waves in the ocean. So we're just going to label some different parts of this wave as we go along, and these first ones should be ones that we recognize. Like that gray line in the middle, Mr. Willauer told us was the equilibrium point. It's also sometimes called the equilibrium axis, right? It's just that line, the rest position of the wave. So you may have heard these next two terms before. The tops of the waves, these orange dots I'm drawing, they are called crests. It's the top or the maximum position of the wave, these guys. So similarly, the tops of the waves are called crests, and the bottom of the waves, these red dots, these bottoms of the waves are called troughs, those guys. So you probably heard crest and trough before. Tops of the waves are crests, bottom of the waves are troughs. Every time the wave crosses the equilibrium point or the equilibrium position, these pink dots I'm drawing, those are what we called nodes, which I'm not really sure how that word came to be, but it's a node. Crosses the rest position. So I'm going to keep this drawing as we move on to our other definitions here. I'm going to move it up into the corner and make it smaller so we can reference it for our other definitions. Our first definition that we're starting with is wave speed, which if you think about it, the speed of a wave, right, we can kind of interpret the definition. Specifically though, wave speed is how quickly a given point on a wave moves through the medium. Mr. Willauer explained what a medium is. So how quickly a given point, what does that given point mean? That means like how quickly is a crest moving through the medium? How quickly is a trough moving through the medium? So we'll talk a lot more about speed and velocity in our next few units, but the units or how we measure wave speed is in meters per second, or m/s. Meters per second, how fast, how quickly something is traveling. That's speed, wave speed. Our next definition is wavelength, which similarly we can kind of interpret that meaning, the length of a wave, but specifically in physics, the definition of a wavelength is the distance between successive points on a wave. Now, what does that mean? Successive points means like between crests or between troughs. So the wavelength is the distance from crest to crest. So that distance right there. It's also, though, the distance from trough to trough. Those two distances are equal. Crest to crest, trough to trough. It's also the distance between node to node. However, it's not just those two nodes that I dotted right there. The successive nodes are actually like one after the other, which is kind of tricky. We'll come back to that at a later time. But node to node, crest to crest, and trough to trough, that's the distance of the wavelength. So remember that successive point can be nodes, it can be troughs, and it can be crests. Put those colors in there to remind you. If we are measuring a distance with wavelength, that means it's measured, or its units are meters, which we just abbreviate with m. So we measure wavelength in meters. Similar to wavelength is amplitude. Amplitude, we can't really infer that definition from the word, but the amplitude is the maximum displacement from the equilibrium point. Now, maximum displacement, what does that really mean? That's sort of like the maximum distance away from the equilibrium point. So that's more of like a height scenario. How tall is the wave? What's the maximum height that the wave reaches? So what we like to say about amplitude is that it's from rest to crest. Rest meaning the equilibrium point to a crest. So that means amplitude would be this distance right here, the height from the equilibrium point or position to a crest. However, it's also the height can be to the trough, right? So from the equilibrium point to the trough is also the amplitude. Amplitude's a distance, which means it's also measured in meters like wavelength. We abbreviate that as m. If you need to pause the video right here, you can to finish writing up these definitions. I'm going to erase them to continue on with frequency. So frequency is a really tricky word to describe in physics. But if you think about the word frequent, like how frequently is something happening, how frequently do you eat pizza? If you're Miss Nielsen, you eat pizza like at least once or twice a week. How frequently is something happening? Well, frequency in physics is very similar to that. So how often is something happening? That something being a wave. So frequency is the amount of cycles of a wave over a period of time. So again, this is kind of a tricky definition, but let's say I was timing this wave. I was standing in the ocean, timing this wave as it passed by me. How fast does the crest to crest passed by me. How long does that take, right? How many crests would pass me over that period of time? That's the frequency. How often is the wave happening over a period of time? So because of this kind of weird definition with frequency, it's a very weird topic, we have weird units. We measure frequency in 1/seconds, or more common for our physics classes, we measure it in Hertz, which is Hz. Hertz is just 1/seconds. It's just named after a guy in physics, Hertz. So frequency is measured in Hertz or 1/seconds, right? Cycles per second. Next up is period. And if you notice, period is actually in the definition of frequency. It's right there. It says a period of time. Frequency and period are very closely related, and we'll talk about that here in a second. They're almost like opposites of one another. So the period is the time it takes to complete one cycle of a wave. So frequency is how many cycles occur over a time period, but the period is how much time it takes to complete just one cycle of a wave. So they're kind of opposites. So how much time does it take to get from crest to crest? And time is measured in seconds for us in physics. So we abbreviate that with S. Period is measured in seconds. How many seconds does it take to get one cycle of a wave? So frequency and period, like I said, they are sort of opposites. But what we like to use, what word we like to use in physics is that they are reciprocals, which you may remember from your math class. Frequency and period are reciprocals because, especially if you look at those units, 1/seconds, that's the reciprocal of seconds, right? So it's just flipped. They're reciprocals of one another. They're just opposites. And we'll talk a lot more about this relationship as we get into our more problem-solving thinking later in this unit. But that is kind of the relationship between frequency and period. So I get that this was a really long video today, but there's a lot to introduce you to in the world of waves, and we're so happy that you're with us in this new world. Back to you. Thanks for watching Physics in Action today. Just want to check with you. Did you take notes? If not, you're free to watch this video once again. Thanks for joining us today. I'm Miss Nielsen, Physics in Action.